find your blots, at least most of the time. And it's not the calcium we care about when we're using milk in a blocking solution for a Western blot, it's the casein. And in case you're trying to blot for like phosphorylation, you might want to use BSA instead of skim milk, although because that casein, it's typically phosphorylated, and then this can cause false signals. And the point of using a blocking solution in a immunoblot, like a Western blot, is to basically make it so that the background is lower. On one of these Western blots, what you're trying to do is you take proteins and you separate them by size, and then you transfer them to a membrane. This membrane is typically nitrocellulose or PVDF. What's going to happen is that the proteins are going to be like present in like different spots on here, and they'll be on like, because there were lanes, they're going to be like lines, but you're not going to see them because they're going to be hidden, but they're going to be transferred onto this membrane. And you'll have these distinct spots where there's different proteins, or these distinct bands where there's different proteins, but remember these bands are invisible, and we're going to make visible the ones that have something that we're interested in using antibodies that are labeled, and then those are going to bind to the thing, and then we're going to be able to visualize it. What happens though is that there's a lot on the region on here that has no protein, or it doesn't have the protein you want, and even the regions that do have proteins don't have the proteins you want. There's that one little region that has the protein you want. And then you have your other regions. And if there's a protein there, it's okay because, well, that's just going to not react with the antibody. But if there is just blank membrane, well, then the antibody is going to bind to that. Because what are antibodies? Well, they're little proteins that recognize other things like proteins. So if we're using a protein to try to detect a specific protein, we don't want the protein we're using, the antibody, to actually just like stick to the membrane. And the reason we use these membranes is because they're really good at sticking to proteins. And since our antibody's a protein, we got to make sure that this membrane is coated with proteins everywhere, even the regions there weren't proteins in the gel. And this way, the antibody isn't going to stick just willy-nilly to here and then cause signal. And so just a technical note, when we're talking about these antibodies, we often do like a primary antibody and then a secondary antibody. The primary antibody recognizes the thing that you're looking for, and then the secondary antibody recognizes the primary antibody, and that secondary antibody is labeled. And this allows you to see it, and it allows for like amplification of the signal because you can have multiple secondary binding the primary, and then you don't have to have buy a labeled primary, which is going to be way more expensive because not many people want to look for that specific protein, but a lot of people will use the secondary antibodies. Much more on this in my Western blog post. But basically, you don't want either of those antibodies to bind to the membrane because one way or another, you're going to get false signal. You're going to get background. It's going to be all like dark, and you might have specific bands that are showing up, or you might just have like the background. And to get rid of like all this like weird background stuff, that is why we use a blocking solution, and we want to block this with just like generic protein. So we can use like a single generic protein, like BSA is commonly used. Bovine serum albumin is kind of just like a blot protein that you can get a lot of pretty cheap. But when typically what we're doing is we actually just use milk, like skim milk. So if you walk into any biochemistry lab, you're likely to see some skim milk sitting on the shelf. It might be actual just like from the store skim milk, like that's what I used before, or it might be disguised as like blotting grade blocker. But then if you look at the instruction, the details, it's non-fat dry milk. And cool note, but to actually like defat milk, they like spin it, they centrifuge it, and then the heavier stuff is going to sink, and then they can separate out the milk, and then dehydrate it if you want to get powder, and then you make the solution. So often what we're doing is with milk, people use from like a 1 to 5% solution. I typically use like a 1%. If you then see high levels of background, you might want to up that percentage. But if you up the percentage too far, it can actually kind of like mask your protein if it's kind of sticking on your protein. And then your protein band will get lower, and then you might want to lower the milk percentage, etc. Another thing percentage-wise is this TBST, the percent of the tween 20. So TBST stands for tris buffered saline with tween. And the 20 has to do with like the length of these different chains on this detergent. So this is a detergent, it's an artificial soap. And what it's going to do is it's kind of going to make things slippery so that they're not going to stick just like willy-nilly anywhere. So basically detergents are really good at keeping things from interacting with each other if those things don't really like each other that much. So a lot of times things kind of clump together because of like they're hydrophobic region. They have hydrophobic regions. So regions that are avoided by water. Water is really like an exclusive clique in terms of water's network. So water forms these really strong bonds with one another, with other water molecules, because it's highly polar. It's got those like positively charged hydrogens, the negatively charged oxygen. At least this is like partial charges. It's got this polarity, but not full charges. More on that in other posts. But basically, water's really sticky, and so it'll form these water-water networks. It'll let things into its network that it likes, things that have charge or partial charge, so hydrophilic things. Whereas hydrophobic things, things that avoid water, those tend, or that water avoids, basically the water clinches up around them and those things get kind of squished together, and you end up with them all clumping together. So if you think about how soap works because it has hydrophobic parts and hydrophilic parts, and those hydrophobic parts can clump up around hydrophobic other stuff like dirt and grime and all that stuff, and then the hydrophilic parts, the parts that water likes, hang out on the outside, and you get like bubbles of things around the gunk that can then get washed off. So by having these regions that can bind to parts that might just bind to other things non-specifically, but keeping those things soluble, the detergent's kind of able to prevent things from just sticking willy-nilly. And this is going to be important to both make sure that your antibodies are binding specifically to the thing that you're interested in, and making sure that like your BSA or your casein or whatever isn't just clumping to the proteins that are on the gel. So we typically, in both our wash and our blocking solutions, have some detergent. I'd just say 0.1%. So 0.1% of the between 20 is common. Typically somewhere between like 0.05 maybe to like 0.2 or so. Note about the detergent is that the detergent is really viscous. So this is tween 20. So it's really gloopy. If you're just making, so typically I make like a liter of TBST, and I just pipette really, really, really slowly into here. I'm not too worried about precision. And if it's a little or more or less than a mil, that's not a big deal. More on my other posts on pipetting viscous things. But if you really, really care about precision, what you can do is you can actually make like a 20% or a 10% tween solution. That's going to be a lot easier to pipette. You can do it by like weighing out or that sort of thing and using the density if you want to get all specific. This can be good if you're just making a small volume of something where little errors in the pipetting, that little bit that sticks to your pipette can really make a difference. Whereas if it's a mil to 1,000 mils, it's not that big of a deal if a tiny little drop is getting stuck. So that is the detergent. Oh, in terms of the milk, so percentage here is a weight volume percentage. So I made a 1% solution, so I did 1 gram per 100 mils, and I made 200 mils, so I did 2 grams. So basically with weight percentage, 1% is going to be 1 gram per 100 mils. It has to do with the density of water and stuff, and I have a whole post on that, and don't get me started about weight percentage, but 1 gram per 100 mils is going to be 1%. So what you're going to do is the first thing you're going to do with your membrane is going to be, you're going to block it. Or you might rinse it off first. But when you block it, it's really important that you take your membrane, so the proteins get transferred on, and you take your membrane and you stick it directly in, so that the part where the proteins are bound are facing out, where they're going to be in contact with the blocker. Then you can pour some blocking solution on. You want to make sure that it's totally covered, and then you can let it rock. So you want to do some sort of like, or typically like an orbital platform, like an hour at room temp, or like overnight in the cold room, depending on your timing and that sort of thing, because then you're going to have to do a bunch of your other blots and your probing and your washes and all of this stuff. But make sure that the protein side is facing up, and block. And you might sometimes have problems if you go too high with your milk percentage, especially, or maybe one of the reasons why like this is like blotting grade or whatever is because it's not all chunky. But you can end up with problems where you get like milk particulates and stuff making it all grainy. And so you can filter the solutions, but be warned that they're not, you need like a filter with bigger pores, or else things are not going to go through. And that is the basics of this. Yeah, so then I like store it in the fridge, and so nothing grows in it. And that is the basics of blocking. Oh, the other thing, so about the BSA. So the BSA, typically people start with milk because, well, it's cheaper and it typically works. One of the things about milk, though, is it's got a bunch of different proteins in there. And whereas BSA just has a single protein. Your antibodies have a chance to like cross-react, so they might bind to things that are not what you're looking for, and they can bind to different proteins, such as the proteins in your blocking solution. So you could actually have like non-specific binding of the antibodies to your blocking solution, which can be a problem in some cases if you're unlucky with your antibody, and so that could cause a high amount of background. One way to test for this, if that's the problem, is you can like make a gel without any proteins on it, like just make a fake, like take a membrane and block it, and then use your antibodies and see if you're getting signal without any proteins there, and that could indicate that it's your blocking solution that's the problem. And so yeah, so then you could turn to like a BSA. Some people use things like fish serum and I don't know, various things that are less reactive. They also have like purified versions of things, the proprietary stuff that they'll sell you. But typically milk works just fine, except you don't want to use it if you're using some sort of like biotin conjugated thing, because milk has biotin in it. So if you're using some sort of like streptavidin detection system or whatever, you don't want to use milk. Another time you don't want to use milk is if you're probing for phosphorylation, because proteins in milk have a bunch of phosphorylation, and then the antibodies that are trying to recognize phosphorylation will be like, oh hey, there's phosphorylation, but the phosphorylation is coming from your milk. Fun note, casein, so the protein, like this protein in milk, well, I mean, there's a lot of proteins in milk, but one of the main ones is casein. Casein is one of those proteins that gets phosphorylated, and the kinase, so a phosphorylator I studied in grad school, is called casein kinase. Casein kinase 1 alpha, by the way. And basically it was a misnomer, so it's not actually, it can phosphorylate casein, and that's how it was originally discovered, but it doesn't naturally phosphorylate casein. Yeah, so fun note, but I've got a connection to casein that shouldn't be a connection to casein. But anyway, that is the basics of blocking, and good luck with your blocking, good luck with your blotting, and hopefully mine looks okay too.